Thanks for the introduction and for everyone for joining. I know the title of this is a mouthful. It's a mouthful in part because this really can apply to a really impressively wide range of things that are relevant to what we're trying to do when it comes to coastal projects. So I'm going to spend a little bit of time in the motivation, a little bit of time in the technical details, and then basically the whole second half of this will kind of be a how have we applied this? Because I think that it is informative to see examples, and that makes you realize just the breadth of what can be done. So apologies for that mouthful, but it'll make sense by the end. As Marissa said, I was one of the original developers of this actually during my PhD. And then early on in FY23, I was part of Jan Ding's project, and we had some internal funding through CODS to take that and mold it a little bit so that it could predominantly run on Army Corps data sets, right? It was focused on using things like the wave information studies and kind of writing the automated script so that we can make use of different data sets that the Army Corps has put an emphasis on. And now since FY23, this is vastly majority, like primary of all the funding has actually been reimbursable military money. So I know that there have been a number of times where we've had discussions about, civil works developments that could transition into military. This is actually something that's kind of more the reverse because the predominant funder has been reimbursable military projects, mostly those that are worried about how do we do soft engineering with nature applications to protect installations? So a lot of the development has been, and application has been on that side, but certainly with some sort of future potential application back into our civil works portfolio. So let's start with some of the motivation. I know no one in this crowd needs this quite as much, but I do want to hammer home the point, and that's that we've put a lot of emphasis on being able to do well with extreme coastal storm hazards. These are the multi-billion-dollar hazards that occur on our coastlines. This is why we have the coastal hazard system. It's rightly been our primary focus for decades. If we think about the future, the current projects that are being built, the conditions that they are going to have to face, the higher water levels, the waves as a result impacting a slightly higher elevation. These are persistent and increasing problems that we're going to be facing moving forward. I have examples on this slide from a town in North Carolina and then in Miami, where you're looking at beautiful sunny days and flooded streets, right? And so consequences to infrastructure, consequences to the dollars that need to be spent in that local area. That's a consequence of water levels that are at multiple timescales in terms of seasonality and king tides and all the different longer term water level components that all add up, these non-tidal residuals that are in the background. And then there are regions in our country that, in addition to water level increases, are experiencing subsidence that's going to lead to this persistent background problem. Maybe we've diverted sediment. Maybe we've extracted groundwater. This is actually a problem around a great many of our coastlines that we have this relative sea level rise, local relative sea level rise that is actually higher than what the global averages are. And then we have shoreline erosion that is not just something that's due to sea level rise. There are many coastlines in this world, and especially around the United States, that with zero sea level rise would be erosive. They've been erosive on geologic timescales. They've been erosive before we ever built a single structure on them. And now we want to try to arrest them because we've built properties there. And so we have many shorelines that are erosive, could accelerate to erode. We are trying to arrest them with, in many cases, these soft engineering solutions like nourishments and that could be both on the open beach or up in the dune. But these protection measures, hard or soft, are are trying to arrest a shoreline that has probably been eroding for much longer than we've ever been present. All of that paints a picture of this really immense length of coastline that needs protection, not just from extreme storms, but from these background things. We need the ability to forecast not just the future conditions that those shorelines are going to face, but also the morphology change that they would face as a result of those conditions. That's kind of a two-step process there. We need to be able to trust those modeling so that we can actually see life cycles of these different soft engineering structures. That's the only way that we're going to be able to prepare things like budgets for future timelines, or be able to really identify the worst case scenarios where it's like time to retreat from this location. We have to be able to see multiple iterations of what the future could have in store, ideally in some sort of probabilistic sense, so that we can begin to put confidence around this. We can't just believe one high fidelity simulation in the future, because the reality is that these are a stochastic process. So that's where that stochastic word comes into the title, and I'll use that more over the rest of this. We care about a different roll of the dice of the future and how that might downscale into the decisions that we might make. Okay, we do actually think about life cycles. So I should give us, credit where credit is due. Historically, this has been done in BeachFX. It's being rolled into the future chart. Life cycle modeling of the beach, though, is a relatively low fidelity component of what we try to project out into the future. So I have an example here on the left-hand side. You're looking at the beach width. This is a prediction that would come out of BeachFX. And there's with time, and a storm occurs, and then there's the following recovery. And that's actually a tunable parameter that is in the modeling framework, and the default is something like 90% in 2 weeks. But this kind of gives you an ideal sense of what we currently do for our fidelity modeling. And if we actually look at what happens in the real world, I now am using a Dune LiDAR data set from the last 8 years at the Field Research Facility. This is basically the highest temporal and spatial resolution of coastal erosion and recovery processes that exist in the world. I can actually begin to look at the real world data that would kind of make up one of these synthetic erosion and recovery timelines. And over on the right-hand side, I have 4 different examples where you're seeing the storm at day equals 0, and you're seeing how long it takes for the beach to recover to its starting shoreline point. The point that I'm trying to make here is that, well, there's really not that much consistency. So, our tunable parameters, whether we set it at 2 weeks or 3 weeks, there's a lot more happening behind the scenes, and that really shouldn't come as any surprise. Recovery processes are dependent on what waves and winds we see following a storm. And although it's tempting to take something like an average background climate, the reality is that that's just not high enough fidelity for what we likely will need in the future, because there's a great many factors that are actually contributing to this. I have a plot here now of the cumulative wave energy that is between storms at the Field Research Facility, where time is on the bottom axis and the wave energy flux in a cumulative sense is on the y-axis. And if I zoom in on just this lower left corner, which is the first 1 month or 32 days after a storm occurs, you can see an order of magnitude variability here in our wave energy flux, right? And so that's going to directly downscale into the timelines that it takes for our beaches to recover from. So it's that interstorm weather that is actually leading to a different response. And this is not just a morphology or a wave energy problem. This is true for every component of what our meteorological and oceanographic conditions could be. So in this example, I'm just trying to highlight that it's more than just a waves and a water level. On the left-hand side, this is a figure that is from a recent paper in 2024. You're looking at a total water level time series from the last 45 years. An annual maxima in blue is picked off, and then this one red dot is now shown over here in this time series, where you're identifying all of the different water level components that are actually leading to this one total water level, and looking at now in a bar graph form the relative percentages of each of those different components. And so that's, the storm surge is some portion, but there is some background sea level anomaly. There's some background seasonality. These are processes that are coming from the temperature of the water. They could come from the Gulf Stream, creating an eddy that spins off towards the coast, and as a result, you see a bulge of water. These are these larger scale oceanographic processes that, in their summation, ultimately leads to a more drastic event. And over on the right-hand side, I'm showing now this same kind of bar graph form of way of looking at the relative contributions to a particular extreme. And I'm showing that for along the entire West Coast. Mostly as a way of emphasizing that, when we spread out and we look at in the large scale, there's a longshore variability, and there is some relative dependence on all of these different water level components adding up to making our potential events that we need to care about. And ideally, we need to be able to model all of these as we move off into the future. So our goal here, we're going to try to see alternate versions of the future. We're going to try to see continuous time series, because that's really what is driving these morphologic responses or these nuisance flooding situations. That means we want to see wave and water level components. That's mostly what Yan Ding showed to you a couple weeks ago, so I'll touch on that. But there's other things that we want to see. We need to see the winds if we want to be able to evolve dunes. If we want to work at all in the cold regions, we need to be able to see things like sea ice and air temperatures. If we want to do anything that is in an estuary or has to do with maybe urban flooding, then we'll need precip and river flow. And we'll actually need to do all of it quite well if we want to do, wave-driven flooding at the near shore and some of the storm impacts that come from this compound space, where you have multiple water levels, waves, and precip all acting together. And ideally, the reason for doing this in this space is so that we can hand it off to things like the models that I'm showing on the right-hand side, right? These are our impact models, whether it's a GenCade model like up here in the upper corner, or it's trying to do something that's even higher fidelity and includes things like Etch Beach or the Aeolus dune evolution model. We need the input conditions to be able to drive those. And so that's our goal here, is we're going to create those input conditions. So the concept, we have seen enough variability in our historical climate that we actually could use weather as the primary predictor of these downscaled parameters, right? Every single one of these, the winds, the waves, the water levels, the sea surface temperature anomalies, the precip, all of that essentially is just a product of weather. So if we can do a better job of seeing alternate versions of weather sequences, and if we can do a good job of associating those conditions with weather sequences, then we're actually onto something here. We can start to make new chronologies and see how those downscale into what we care about. And this is not a crazy new concept. I have a paper from the 90s here on the bottom about stochastic weather generation, and there's a review already of stochastic weather models back then in the 90s. It's gained a lot more favor in recent times, and I have a couple screenshots here from the big companies, right? Google and IBM. Like, one of the reasons this is being picked up is because it's an application that is really ideal for AI and ML applications. So I hope over the course of this, you'll start to see what I mean by that. But we're creating statistical relationships, and that can be done quite easily with some of the new machine learning and AI applications. And that's one of the reasons it's being picked up by these big companies. So the assumption, weather drives the local forcing. right? It's the thing that creates the friction across the ocean surface in the form of wind that then creates those ocean waves that then pushes that water towards the coast. You know, like these are proxies that represent the local process. So if I look out into the ocean at any one particular time, I can see a weather pattern, in this case, sea level pressure pattern. And associated with that sea level pressure pattern, there should be some kind of relatively constrained distribution of conditions, call it the waves that are generated by those winds, that when I see that pattern in the future, I should be fairly confident that I'm going to see this subset of the full global climatology of possible conditions. The idea is that we should be able to pull it apart, right? So now if I see a slightly different weather pattern, I should see a slightly different distribution underneath it all. And ideally, if I see those sequences of weather, then I should be able to see those sequences of downscale possible distributions. In a nutshell, that is what we are really trying to do. We have to do some tricks to really confidently separate that weather apart. And we need to do some tricks to statistically associate the distributions within each weather type correctly so that we're sampling from them in a quality and realistic way. But ultimately, we're going to try to take the historical weather that we've seen, break it all down, associate its distributions, and then figure out a way to simulate this portion before we then simulate the downscale parameters. So the data-driven sequencing model that I have used in the last couple of years, what you saw in Yan Ding's presentation, is an autologistic regressive model for creating the synthetic time series. This can be done with temporal convolutional networks. It can be done with a number of different approaches. The ALR model is a little more explainable, I guess. You can directly see some of the weights that are produced within it. But this is really just a very fast statistical method for creating sequences. For starters, we're going to reach into our historical climate and pull it apart in an automated way. This is called weather typing, and weather typing is not something new. Started in atmospheric sciences as far back as the 80s and 90s and started moving into something that coastal scientists were taking advantage of probably about 15 years ago, and has kind of steadily evolved over the years. The idea is that I look at every single daily sea level pressure pattern. In this case, because this is for the field research facility in North Carolina, I'm looking at the Atlantic Ocean. This is where not only local waves, but swells are being generated that could affect North Carolina farther out in the Atlantic. So we're going to look at the whole ocean basin. We're going to perform a principal component analysis. Then within principal component space, we'll perform a clustering called k-means clustering. So every single day is getting reprojected into this lower dimensionality space as a single dot, a single point. And then when we cluster in this, ideally, we should be kind of grouping days that look very similar in the historical record. And if I take a centroid of, say, this orange cluster of dots and reproject over into this space, now I am getting kind of a representative pattern of those couple of hundred dots from the historical past that fit within one of these clusters. Okay, so now when you look over on the right-hand side, in the lower corner of each one of these, that's the number of historical days that have been stuffed into that particular weather type. We know when those days happened in the past. So in this case, a breakdown of ERA5 sea level pressure patterns. That gives us 45 days worth of a record. I know when December 1992 fits into this, I go and I get the waves and the water levels that occurred on that date. And now this is how I'm able to create my sub-distributions within each of these, is because I've seen 500 plus examples of this in the past. That means I have 500 plus samples to create my distributions from. Because I know when these have occurred in the past, I also am able to start thinking about their conditional probabilities of occurrence, right? We need to create a synthetic weather model, and that's not just saying I've seen yesterday's weather, can I predict tomorrow's weather? That is also understanding the conditional dependencies on larger scale processes. So I have an example here of seasonality. This simply says that in some future simulation of this weather, these days in the upper portion of this grid, where every single day from the historical record is fit within a bin, these days happen much more frequently during February, March, and April than they do during August, September, October. They're essentially my winter weather types rather than my summer weather types. So in some future model, when it's stitching things together sequentially, it should know that in the summer, you can't possibly select from this upper portion. You're much more likely to select from this bottom portion of my matrix of possibilities over here. And then just to give you a better sense for what's happening within all of these, we are isolating particular behavior within each of these, right? So an example here is simply that I'm identifying the probability of storms that are occurring within each of these weather types, specific in this case to the field research facility. And there are many different ways that you could classify a storm that might make the heat map over here on the left look slightly different. But the point of emphasis here is just that we're doing a better job of isolating different storm types into some of these different weather patterns. That whole idea of trying to create those unique distributions. We're taking that climate and we're pulling it apart, and we're creating storm types within our matrix. And because I have seen the historical record, I know exactly when a storm occurred. I know what weather happened after that day. I know the variety of weather that happened after that day. So now on this left-hand side, I'm showing transition matrices. So following a stormy weather pattern, there's some likelihood of me jumping around to other weather types within the matrix. And that's not only true for 1 day later, but for 2 days later and 3 days later. This is called a Markov chain. So a Markov chain is basically me understanding transition probabilities from one state to another state. A first order Markov chain only knows about 1 day later. A second order Markov chain knows about 2 days later. So these are the additional details that we're going to hand off to our ALL model. We're going to know about seasonality dependence. We're going to know about our day-to-day to day-to-day Markov chain. And we're also going to know about some broader scale processes. This is the Madden-Julian oscillation over here on the left-hand side. Madden-Julian oscillation, in a nutshell, is this center of atmospheric convection that rotates around the globe on kind of a 1 to 2 month cycle. You might have heard about this when people are talking about, the next 2-week outlook for tropical cyclones or for the hurricane season, because the Madden-Julian oscillation has a really important effect on things like the occurrence of hurricanes and tropical cyclones. It can dampen or enhance the likelihood of those storm systems, and it actually, in a broader sense, affects global weather patterns of all types. So this is a process we're going to include because it's sub-seasonal, but is above the day-to-day. So we've got our Markov chain for kind of the short-term evolution. We're going to put the Madden-Julian oscillation in at the sub-seasonal. We're going to have seasonality. And then our largest scale is sea surface temperatures. This is how we account for El Nino cycles and the Atlantic overturning oscillations. These are large-scale processes that are often on, El Nino, that's like a 5 to 7 year period. The AMO, that's actually more on like a 25 to 30 year cycle. These are the things that are slowly modulating climate in the background. But we've seen enough over the last 45 plus years that I can create a statistical conditional relationship between a particular daily weather type and these larger scale sea surface temperature processes as well. So now as we simulate our future climate, we are going to simulate these processes off into the future. And in a certain El Nino year in 2052, we now have a subset of weather patterns that are more likely to occur that year and another that are less likely to occur. So multiple scales are being thrown into this. An ALR model has coefficients, so I'm going to call that X sub t here, and interannual coefficients, those are the sea surface temperature anomalies. Seasonality, that's a cosine and a sine wave that's just associated with the day of the year. And then some sub-monthly components, that's that MJO, the Mann-Julian oscillation. These things are all going to feed into conditional coefficients. And we're going to create a probability matrix where we are adding that Markov chain at a daily time scale. So the, technical discussion, got to show you one formula. This is the math that's happening behind the scenes in the probabilistic sequencing model, is that we are giving ourselves some sort of understanding about each of these larger scale processes as we then make a choice every single day in a synthetic record of the weather that can occur on that day. And this is just showing you an example of how we then are able to create synthetic years and how those synthetic years make sense. I've colored the continents in the lower left-hand corner of each of the weather patterns. And now to the right of that, you're seeing across 100 different simulated years how we land on the one-to-one line, comparing our historical probability to our simulated probability. But although we are landing on the one-to-one line in an average sense, we are seeing variability. These are box plots that show, a range of possibilities. And that's a little bit of an art form within this, because you want to see a lot of variability, but not too much variability, right? Like you want to be able to roll the dice and see slightly different weather year to year, but you don't want to roll the dice and see something unrealistic. So this is what we are looking for in a typical simulation, is some sort of variability about the one-to-one line without our means falling way away from that one-to-one line. Hopefully that's making sense. It's all about seeing a different synthetic future. Looks like I've got a figure that dropped off here, but once we've simulated weather, we need to be able to downscale. And there's actually a bunch of different approaches to doing this. I'm giving one example here from a 2021 paper that refers to every single variable that you're downscaling as a hydrograph, right? So you look into your past record, you find a particular daily weather type, you extract, say, the wave height time series that occurred within that, and you create a normalized hydrograph of that wave height. And you then stretch that hydrograph in the future simulation by making a random sample from those distributions that we have binned into each of our weather types, right? We created those unique distributions on purpose. That's how we're pulling the possibilities apart into these unique subsets. Now we're going to sample from those to stitch ourselves back together. An example of that, this is a figure that is from a paper just published this last year. But over here on the right-hand side, with each of these different weather types, and this was actually for a location up in the Arctic, we have a distribution of maximum HS and minimum HS that is possible within these different weather types. And so when you have your historical storm hydrograph and it's been normalized to 0 to 1, and now you move off into the future and you are simulating the minimum wave height and the maximum wave height within that particular storm weather type, these are the populations that a copula is fit to that you're then sampling from. Hopefully that makes sense. We're trying to see variability, create variability, but keep that variability realistic. So now here's an example. This one's actually from the original work that I did at the end of my PhD, where we have 500 years sampled. And across the top, you're seeing annual weather types. So in that case, the red ones, those are El Niños, the blues, those are La Niñas. We're just trying to see the full variety of climate forcing. And how that ultimately downscales on the bottom to a total water level. And that total water level is all of the different water level components, from tides to seasonal components to water level to the storm surge, all being added together with then a run up on top of them. And the blue dots are the annual maximum, and that 1% exceedance event, that would be the 1 in 100 year event in a 500 year time series. That's your 5th largest event, but it's your 1 in 100 year event in that synthetic 500 year time series. If I take all of the different variables, so wave height, period, storm surge, monthly mean sea level anomalies, tide, and run up, and I plot, now in this case, 100 different 500 year time series. So now I've got annual maxima plucked off of every single one of those synthetic time series, creating these large blobs of possible annual maximum events. And now I am pulling off the 5th largest event. So I have 100 1 in 100 year events plotted in red. I know that's a lot, but essentially what I'm trying to tell you is that I've done a synthetic climate 500 years, and I've pulled off the 5th largest event from each of those. And the point I want to make here, they're actually fairly variable. All of these red dots do not just cluster together. What does that mean? It means our 1 in 100 year event, that these red dots are not clustered together, that these red dots are variable, that a 1 in 100 year event from one simulation to the next is not exactly the same. That when we try to simulate the future and we take, say, one crazy big storm and put it on top of really that you need to be able to simulate a variety of future conditions, because our attempts at a 1 in 100 year storm, we can't just believe one high fidelity simulation. There are a whole bunch of different versions of what a 100 year storm could do to you. And the relative amount of a still water level component versus a wave component is going to lead to a different downscaled impact. So hopefully this is still sharing.
Yep, you're good.
Okay. That's the extreme part, but then the whole point here is that we are creating time series of conditions that can be used to hand off as model inputs, right? So now in the lower right-hand corner, I'm just trying to emphasize in a kind of cartoon form how, you know, we're within these time series of total water levels, we're creating a tide level and a storm surge, and we have wave characteristics, and these are all the things that we would actually be able to hand off to a downscaled modeling system. Yan Ding, I believe, showed this to you a couple weeks ago. This is an example in Abscon, New Jersey, where you are looking at COSAT, so that is a satellite way of extracting shorelines in blue for a shoreline that has experienced multiple beach nourishments. And then in green, you're seeing some local transect survey data. So those are all plotting quite well together. And then what you're seeing behind the scenes is Jan and I did 100 different Monte Carlo simulations. And in gray, this is the full width, the full variability of all of the simulations that we ran. And in black, you're looking at the average of all of those simulations and how that average has really collapsed down into something that the realistic simulations fairly closely followed. And then it's also worth mentioning that all of these blue dots are still landing within the width of our gray dots. And in that sense, we're saying that we saw a probabilistic range of conditions that could have occurred. And lo and behold, our observations actually do land within that. So over on the right-hand side, this is an example where you can reach in at any one of these times and you can extract a probability distribution associated with where the beach might be at that time in the future. And then what Jan also showed is that you can couple these with more than just GenCade. So in this case, for CIRP here, it's worth including the inlet reservoir model coupling that he performed, where now you are experiencing infilling and measuring the amount of bypassing volumes that is happening for Absecon Inlet. And now over on the left-hand side, we're seeing the variability in the volume of that sediment that could happen across all of our simulations. The point of emphasis here is that you see a range of possibilities, and this is not possible without a continuous hourly time series of the wave directions, right? That thing that is really controlling the bypassing of sediment volume, the alongshore transport of the sediment volumes. So if we just added in something like an average background wave direction between storms, these lines would not show this degree of variability. But because we have simulated the weather, we actually are seeing a more representative, a higher fidelity realization of the variability that could occur here. But the goal is to do more than just waves. So published this last year and funded mostly by CODS is an example where Nick Cohen and I connected his dune response tool to this same stochastic condition emulator. So the dune erosion portion of the engine really cared about all the water level components and the run up, adding up to whether or not waves are eating away at the bottom of the dune. And then the dune recovery portion cared about adding all of those water level components, determining how much of the beach was exposed to potential wind fetch. And then in this version of the emulator, we add winds with a directional component so that we can get not only the magnitude of the wind, but the direction of that wind and whether or not sediment is being sent into the dune to recover it, right? So this is an example of a dune that was recovering, experienced a significant erosion event, and then regrew with time. So that's a single example there, but ultimately it's only possible because we've added to this weather emulation model this wind rose component. So now I don't just have things like HSTP and the non-tidal residual, but I also have the things that help dunes recover. And those are conditionally dependent on the different sea level pressure patterns. Now, in this case, 1,000 different simulations projected out to 2100, and we can see how our dunes are going to erode over the long term. So this is putting a life cycle on top of dune evolutions. And on the right-hand side, this is kind of the summary figure where Nick looked at how that is actually varying in the alongshore throughout the East Coast. This is an example that is a completely external collaboration. This is working with Dr. Matthew Brand from LSU and his student Yusuf. And what we're talking about in this case is marsh restoration. So we've taken the continuous time series that is produced by the weather emulator. We've coupled it with Dr. Brand's hybrid model that is actually able to determine how the tidal amplitudes within an estuary change depending on the restoration component. So he's got an AI model that is able to do that. And now we're able to start, in this case for Coos Bay, Oregon, make projections of the kind of the hours of exceedance for water levels on places like US Highway 101. That's the main transportation hub through that town. Dependent, in this case, I know there's a bunch of things going on in these figures, but each one of these is a different restoration example. So a different approach to how you would restore that wetland. And now over on the right-hand side, we can directly translate how the different flooding. Sorry, everyone. I don't think I've had this problem while sitting in this office. Okay.
Not till today.
So
Go ahead.
Another example is trying to move into cold regions climates. So on the left-hand side, you're looking at sea ice, which grows in extent over the course of the Arctic winter and then retreats in the summer. And what does that do? That completely changes the size of the ocean basin next to our sites that we might want to do a project. And that ocean basin changing size, well, that changes the fetch that wind waves can grow over. So that's a process that directly downscales into the conditions that our project might ultimately face. So we did an approach here where we borrowed from another methodology that was recently published in 2023, and we added sea ice. And then on top of adding sea ice, we formed a statistical relationship between the maximum wave height that could be created associated with the fetch or the area of the wave basin that was occurring at that particular time. And so now we're able to make synthetic records where we grow our basin size, and as a result, we allow ourselves to have waves. But then as our basin size shrinks and as sea ice expands and eventually shuts off, we turn waves completely off, right? So waves are this seasonal conditional thing that is directly tied now to sea ice. And in this case, we also simulate air temperatures, because the air temp is going to directly downscale into whether the shoreline composed of permafrost is completely frozen. And so in this case, we're trying to look at the future stability of these permafrost and tundra coastlines. But these are the kinds of time series that we want to be able to hand off to a permafrost erosion model. What you're looking at here are future simulations going out 50 years. And in this case, the E parameter is the rate of erodibility of the underlying permafrost. These are these parameters in a morphology model that we're ultimately highly sensitive to. But we can begin to quantify the underlying dynamics as we investigate the sensitivity, not just to the range of stormy conditions that could affect a location, but also begin to ask questions of the morphology model and understand our future tundra loss as a consequence of these future erosion conditions. So that was a cool paper that we just published this last year and hope to continue working. And that's also something that's not in the civil side of things. For the last 10 minutes, I just want to say that we're working on version 2.0 and trying to conceive what's the future is going to be. So a conceptual limitation of this framework is that you've only seen the variants created in the historical record. But ML, machine learning enabled weather models are exploding right now. And they can now simulate a whole lot more variance than what the last 45 years of satellite observations has provided us. So we have teamed up with the weather effects team here in ERDC. That's like a 20-person group spread across multiple labs. But in particular, we're working with Ted Letcher, Brendan West, Sylvia Garmong, and Sandra Legrand as our main collaborators and points of contact here. The idea being that we can see alternate versions or an increased variance of weather systems and be able to see synthetic storm events and synthetic chronologies coming out of these very efficient weather models of the future. Even more intriguing, we're using machine learning models to hopefully be able to downscale higher fidelity to our local sites. A lot of what I showed you earlier, what Jan and I did, we produced time series of a wave height, period, direction at a local WIS node. And then we needed to create another model that took those 3 parameters and downscaled them to each of the individual transects of the GenCade model. Essentially, because it is not straightforward to downscale a 2-dimensional or a 3-dimensional problem. In this situation, we're exploring how to use a NVIDIA model called CoreDiff. So this is a super resolution downscaler. In the lower left-hand corner, this is an example where they have a particular storm that they're targeting downscaling, taking, in this case, a 1/4 degree resolution weather model. And they're trying to super resolve it to ultimately be able to predict something like the wind variability at 1 kilometer resolution. And we have an example over here on the right-hand side using the military reimbursable effort that we're working under right now, where you're looking at a very coarse resolution wind model that has been, with the snap of a finger, like this happens very quickly and efficiently. Now we are seeing actual downscaled wind fields that are able to account for the local topography, and we could actually get much better locally resolved wind fields to now downscale to our wave models and actually take kind of this larger scale weather concept that we're talking about and really super resolve it to our local site. Just shows you the immense potential that AI has as we move forward. We're also trying to add higher fidelity in what is downscaled. I pointed earlier to, Jan and I using the triplets of wave height, period, and direction. And then we extrapolated those to the transects where we then had on the longshore varying wave height, period, and direction. But that's a limitation. That doesn't have the full spectra. So Trip Collins has been working with us during this FY, and we've been working on a method that allows you to take an offshore directional wave spectra and downscale that. In this case, this is the same location in Maine that you just saw, but over here on the right-hand side, you can get a sense for how we are starting to make predictions of the time-varying evolution of waves, but we're doing so now with the ability to predict a 2-dimensional spectra that is occurring at the near shore. That's how you start to be able to hand off a lot more fidelity to your local scale impact model. When you have the full spectra, as opposed to kind of the 3 primary parameters, you're really gonna start to be able to downscale to a wider variety of local impact models. And just to hammer home the idea of trying to do a better job with spatial downscaling, we're also exploring Cora's historic data set. So the number of data sets in the end, I should say, this whole framework from beginning to end is dependent on data being massaged and statistical relationships being performed across those. And making use of hindcast data is one of the great ways that you can really extend this network. In this case, Cora has time continuous water levels on a mesh grid. So now we can begin to do things like, rather than predicting the water level at one offshore transect for GenCade, we can look at a spatial water level on both the inside of a barrier island and the outside of that barrier island. And now in the lower right-hand corner, I'm just showing that if blue is the historical and yellow or orange is our AI emulator prediction, we're able to now make predictions that know about that spatial variability. And finally, our very last point that I want to make is that we're hopeful to use some of this funding to begin to start considering compound flooding scenarios. There are a number of different models that are able to use GPUs. That means that they actually are fast enough that you can simulate a really impressive variety of storms, and that means that you could create a library of conditions that you could train and use within this stochastic weather framework to ultimately downscale the weather to processes that have to do with things like urban flooding, because now you can account for really fine resolution DEMs and drainage networks that include things like the sewer. That's all that I have for you. I apologize for how many times we got cut off.